Alright folks, we're going to get started here. Gonna fix that lighting there. Yeah, that barely does anything. Yeah, it's a little bit better. Okay, well, obviously I'm stuck here in my office today. I'm already getting internet issues, so I'm actually simultaneously recording this on my computer, and I will be posting that video on YouTube as well, and it'll probably be clearer than what we're getting through Zoom. Who knows how the captions will go? I know Zoom does adequate. YouTube's typically a little bit better, but we do have some pretty big words that introduce in this chapter. Okay, so what we're looking at today is starting on chapter 19, which is labeled more about amines, and it does have a tremendous amount of review. But the new stuff that's in there is relating to stuff that we most recently got. So the aromatic properties and how it affects electrophilic and nucleophilic substitution by putting in things like nitrogen in there. Alright, I'm turning off that video because it does pull back on the computer too much, but should be able to hit this and we should have our chapter 21 problems popping up there. And let me go ahead and start a second version of this so I can write on things if I need to. But question 1, well, 21, is just nomenclature. And so I can do those right on print of the book, that is. Okay, so that's not, well, I know, because I need that one. Alright, so this first one, a couple ways to name that. Probably the easiest way is to name it with the AZA prefix. So the AZA just says there's a nitrogen in it and it defines our number 1 location. So that first one, I'd be saying the ring is a AZA cyclobutane with a methyl in the 2 position. So full name, fully IUPAC, 2-methyl AZA cyclobutane. Following that same technique for B there, 1, 2, 3, so have a 2,3 dimethyl AZA cyclohexane. Can't do that here because this particular ring, because that lone pair going inside the ring, makes that aromatic, and it doesn't actually end up using the AZA prefix. That ring with the nitrogen is just known as pyrrole, and that would be the number 1 position. So this is a 3-chloropyrrole. 2 R's. We can go back to the AZA here. We'd be saying that's the 1 position. So 2, 3, 4, 5. So 2-ethyl, 5-methyl AZA cyclohexane. Alright, now another way we can name these are based on the name that's applied to the ring based on a number of carbons. So a 4-membered ring with a nitrogen on it is actually a azimuthide. So this thing could also be called 2-methyl. That's spelled A-Z-E-T-I D-I-N-E. And 5-membered ring is piperidine. So this one could be called 2,3-dimethyl piperidine. And that would apply here as well. So this could also have been 2-ethyl 5-methyl piperidine. Okay, that next one, gonna have to bring up my piece of paper here and go bigger. I think we'll just go across, so we'll do A, D, G, just so I can keep that paper scrolled down some more. Alright, so that first one, I have a secondary amine with a acid chloride. Let's just go make a secondary amine. The reason there's two is because normally we end up putting that Cl with like an H, but this time it'd neutralize it. So we're going to have, when we're all done, that's still a benzene, still carbonyl, but this will now be that nitrogen. And we'd have another one of these 5-membered rings, the nitrogen. Uh-oh, sub 2. That neutralized that chlorine, or the HCl that came off. Alright, D is an interesting one. This ring, that O having a set of lone pairs on it, that is electrophilic. And I mean it is aromatic. And it will be susceptible to electrophilic aromatic substitution. I know this is BF3 and THF, but you will see that we can actually kind of use those instead of our aluminum chloride and Friedel-Crafts type reaction. So that was A. D does actually do a Friedel-Crafts, but on that 4-membered ring with oxygen, 5-membered ring with oxygen, we find that that 2 position is very attractive. And since that one's already occupied, we're going to put that carbonyl and CH3 over here. And I'll put G over here. Okay, G is an interesting one. I have a diazonium salt. That's that N triple bond. Well, it turns out when I react that with an amine, especially electrophilic, or I can do electrophilic aromatic substitution with it, I will essentially attach this nitrogen to that thing. It's something that was kind of introduced in the last chapter. But what we're doing is this particular nitrogen does activate the 2 positions. Just now that 2 position now connects to a nitrogen, and the other one is still that C6H5. So basically this thing still attaches, but we're going to attach that right there to that 2 position. All right. Well, looks like we are on to B. So on part B, we have bromine onto that substitution, and we're going to treat it with OH with some base. Well, excuse me, I know at first all that's going to do is an SN2 type reaction and replace it. We'd have an OH. But that will actually do like a enol rearrangement quite easily. So this nitrogen will gain the H, and we'll push that double bond there, we'll push that double bond there, and this will go out as an O. Yeah, and we're fine, because this still has a lone pair in there. That is still a p orbital, so we still have 1, 2, 3 pairs of electrons in there. It's still actually aromatic. Alright, E, have a lithium and a chlorine. That's just a coupling reaction. So it's essentially going to be a second benzene ring attached right there. Yeah. Alright, H. I got NH2. Excuse me. What's that second step? Well, that we find out is quite acidic, almost benzylic in nature, actually even more so. So we're going to be able to deprotonate an H off there. Yeah, and then it just does a backside attack. So I'm going to draw this out a little bit more. This stays aromatic, but this would become a CH2 lone pair, and that's going to do a backside attack to our halogen. So we're going to end up with that ring stays intact exactly like it was, but this is now a CH2 connected to a CH2, CH2, CH3. Alright, last row, CF and I. Alright, so C, we have 4 carbons and a bromine. Going to turn into 4 carbons and a CN. And then the hydrogen with Raney nickel is going to turn that into an alkane with an NH2 on the end. Now, this thing is nucleophilic enough, it's just going to do a backside attack. So we're going to get that ring with the nitrogen still there. We're not going to need to lose anything. It's going to have a CH2, CH2, CH3 attached to it and just be positive in nature. And then we can write Br here minus, because that's essentially how it's going to be at first. And finally, I has a sulfur with that bromine. Alright, but after our treatment with magnesium, we'd have MgBr, and then with carbon monoxide, that'd be COO minus, and then the HCl will just protonate it. Yeah, that'll work. All right. 23, we're ranking strongest to weakest. Well, that should be kind of easy at first because I do have some positives and some positive species. So I know all of my positive charged species would be the most acidic. However, that second one there, if I lose one of those, that ring becomes aromatic. So that is the strongest. And I will do 1. Get no benefit whatsoever there. No natural benefit there, and none here. So none of those other positives make it aromatic. We've removed the hydrogen. So therefore, we're just looking at which is the hydrogen most easy to get to. Alright, that's going to be a little bit tighter held because it's a smaller ring. So I'm going to go 2 and then 3. And this would be our fourth. Pi bonds don't help us at all bring that in. Okay. Now the remaining ones are non-charged. That would have a lone pair already. This one would have a lone pair already. And that one's not nearly as useful. Alright, so aromatic and aromatic. This other location helps keep it more withdrawing. So 5 and then 6. And then that's the highest, that's the weakest. That one's going to behave more like just a regular old amine with regard to pKa's. Alright, so 24. Which is easier to decarboxylate? Well, decarboxylate is what we saw when we had kind of an alpha situation. So we had a carbonyl, CH2, carbonyl, because in that transition state we essentially made a enolate-like thing, or an enol, where we moved those electrons down, allowed one of those H's to get kicked off easy enough. Ended up making the carbonyl with the O into a good leaving group. Alright, so okay, let's take this one, draw this slightly different so we can see what's going on. CH2, carbonyl, O and H. So our electrons, I'll do this in red. Electrons can attack there. These can go in here. And those can go there. Yeah, that'd be decarboxylating. That give us a nitrogen that's now double bonded to a CH2. All these, that's not there. That's still double, that's still double. This is now an H and a lone pair on it. Ring's still aromatic though, because 1, 2, 3 pairs of electrons inside. And then this is an O, C, O. Yeah, carbon dioxide. This one I need to be breaking off that bond. Yeah, we're not going to see that. So this one must be the easier one to, because we have a mechanism that shows what that happens. We have that nice little alpha position, carbonyl and carbonyl-like. So an alpha position between two different ones. Alright, now next one we're ranking most to least toward electrophilic aromatic substitution. Now, all of these have that lone pair on them, so they are all activators. And last chapter we kind of left them, excuse me, we left them all in strong activator category. But if I had to rank them, let's see. Well, nitrogen's going to be to donate more, make that more nucleophilic, so it's stronger than the oxygen. It's also stronger than the sulfur, and the oxygen itself between these two would be stronger. So I'd rank them the N substituent more than the O, more than the S. Yeah, more donating capability and more donating capability. So that applies to both these. Alright, that next one, we might end up having to draw something out here. So one of these prefers to go to the C3, which I have put 1, 2, 3, or 3, 3, or 3, and one of them prefers 4. And if I look, I have a nitrogen donating group, carbonyl withdrawing group. Okay, so what I'm going to do here, let's do just the nitrogen ring without a substituent. And we're going to do electrophilic aromatic substitution at the 3 position. So, Y for my electrophile. And the first thing I'm going to draw, have it 1, 2, 3, and I'll move the positive there. And of course that will resonate. Okay. Alright, this does help us, because if I put a withdrawing group right there, it would already be kind of positive, and that would hurt that particular uh, molecule. Yet, if there is a nitrogen here, I get one more resonance structure. Yeah. So because that helps, I do want that donating group right there. So this is the one that favors 3. And let's make sure about that. We're going to do the same type of idea, or same type of drawing, but we'll let the substitution occur at the N4. C4, sorry. But I'm going to go ahead and put this carbonyl compound on here, because the only way this is true is if having it there makes a difference. Alright, so I'm going to have the substituent add there, which would cause that location to be positive. And that will totally avoid putting the positive right next to the positive. So that deactivator is not going to be in our way when we go around and spread that around our ring. So we will make that, put the positive right on the nitrogen. Yeah, gonna go to all those places, and I don't have a problem with the positive being on my withdrawing group. They just end up on the nitrogen itself. Yeah. All right. 27. Benzene undergoes electrophilic aromatic substitutions with Arizonins in the presence of a Lewis acid such as aluminum chloride. What is the major and minor products of the following reaction? Okay. Now we kind of know from the previous chapter and how acids and bases go that that lone pair is going to attack that, end up giving us a slight positive at that location. That's going to be way too bulky to do an electrophilic substitution there. So while that is positive when it's all attached on there, it's also going to share that charge here, I believe. Mainly because that's the only carbon that could do that. Yeah, we'll break that bond, make that electrophilic, and that's what ends up attacking to our ring. So we have the benzene, we're going to attach there. So that is going to be a carbon, and that CH3 that's right there is up. Then we have a CH2 to a nitrogen, and that nitrogen will end up with just a CH3 because we will kick that aluminum back off eventually. That's pretty clever. And we expect similar reaction with epoxides. Well, epoxide does have a lone pair. Aluminum chloride will attack it. We can come in and attack the back side as an electrophilic. Yeah, expect the exact same type of thing. Speaking of that, that might be a better way of seeing this mechanism, or lead to a better way of seeing what's going on this one. So, we have our ring. We know it attacks electrophiles because we're talking about electrophilic aromatic substitution. And we have a 3-membered ring with a nitrogen and a CH3, CH3. And we're saying that first step, the aluminum chloride attaches, and I'm saying the ring becomes electrophilic. Now our nucleophilic benzene attacks it, and under acidic conditions we will end up going towards the more substituted side and break that bond. Yeah. And it might even be good to see that at first you are going to have CH3, CH2 in CH3, it's got an H on it, that's still attached to that AlCl3, but that's going to be able to get kicked off now because it's, well, it's easy enough to kick off because that's just a Lewis acid attacking a base. Yeah. So both our nitrogen and oxygen 3-member rings should get attacked relatively easy by that. Okay. 28. Pyrrole. Reacts with excess dimethylaminobenzoaldehyde. Ooh, there's a mouthful. Benzaldehyde. Para-dimethyl. Okay. Nucleophile attacks electrophile. And we get, I'm going to spin my second molecule around, attacking the second location. This will now be a COH, H, connected to the benzene ring, still connected to the dimethyl amino group. Okay. No. NH from something goes on there, allows this to turn into a good leaving group, and it will. These jump down there, those come up there, and this lone pair moves down here. Giving us yeah. Alright, and then I think it does say excess up there. So I'd imagine we do that again with this side. Get the exact same thing. So both two positions on that ring get filled up with these guys. Okay, so 29. Dipole moments of furan and tetrahydrofuran are in the same direction. One has a dipole moment of 0.7, the other has a dipole moment of 1.73. Okay, so furan, tetrahydrofuran. Alright, driving factor of the dipole moment would be the electron pairs. But two of these on the furan are making up the ring, yet on the tetrahydrofuran they're both outside the ring. Alright, so a lot more electron density. This has got to be the high one. That's got to be the low. Yeah. All right. Naming these guys, 30 really, or 30A only really gets one name because the 6-member ring with nitrogen that's aromatic is pyridine. That'd be 1, 2, 3, and 4. So I'd say this is 4-chloro. 3 isopropyl, pyridine. Alright, going to do this where we're naming this as an aza. So it's an azacyclopropane 1, 2, and 3. Yeah, we'll do it that way. Isopropyl comes before methyl. So 2 isopropyl, 3 methyl, azacyclopropane. And because it's a 3-membered ring with a nitrogen, Excuse me. We could also do the azotide name. So this is a 2-isopropyl 3-methyl azotidine. Four-membered ring with an oxygen. We're going to call it oxocyclobutane. So oxacyclobutane. So that'd be the one position. I have methyls or ethyls. Got two here though. 2, 3, 4. So 4-ethyl. 2,2,3 trimethyl cyclobutane. Excuse me. And just like the rings with nitrogen, we can also simplify this. Instead of saying it's azotine, this is 4-ethyl 2,2,3 trimethyl, and its short name is oxetane. Ooh, that's A-N-E at the end. Okay, 31. It actually is a tertiary amine reacts with hydrogen peroxide to form a tertiary amine oxide, which is this wonderful thing. The tertiary amine oxide undergoes a reaction similar to Hofmann elimination called the Cope elimination. In this reaction, tertiary amine oxide, rather than the quaternary ammonium ion, undergoes the elimination. Strong base not needed because the amine oxide acts as its own base. Yeah, so we have a complex one. Let's see, when we're breaking it off, we're breaking that bond there or this bond. But this would leave us a very substituted alkene. That would be the easiest one, so we always get that least substituted. And it wants to know, does this Cope elimination have an alkene-like transition state or a carbanion-like transition state? Okay. To make this bond break, we essentially need to remove one of these hydrogens. And this base could do that. Yeah, so when it leaves, it's going to be like a lone pair. So that is more like our carbanion-like. Yeah. Okay, 32. Which products are obtained when the following tertiary amines reacts with hydrogen peroxide followed by heat? Okay, this is kind of applying that Cope rearrangement. So, what we're going to expect is we're going to attach an O to each one of these, to the nitrogen that is, and then the bond we're breaking It's gonna be the nitrogen to one of the carbons nearby it. So like on this last one, it shows all of them. One of these is our potential breakage, but we need to actually break it and create an adjacent double bond. So that actually eliminates methyls from being broken off. So it's got to be a carbon that has another carbon attached to it, at least an ethyl. And our potential double bonds that are formed, would need to be the one with the most hydrogens attached. Okay, so let's look at this first one in a little bit more detail here. So, well, that one's kind of an easier one because I can't break this one off or this one because they're just methyls. So I know that the part of the nitrogen that has the oxygen on it is this, and that location that was a CH2 stays a CH2, but this, which was one more away, we lose an H off that. So that's our two products. We kind of do the same thing on B. It can't be that carbon gets ripped off, so it must be this one. So we know that one of our products is a CH3 connected to a nitrogen that's now an OH that's still connected to a benzene ring. And that CH2 is now double bonded to a CH and a CH3. All right, I'm going to expand C so we can see what's going on because there's two possible breaks. The reason there's two possible is because it's either going to be this side breaking off or this side, because both of those have additional CHs. So we're either going to make a CH2 double bonded to CH2, and then everything else over here is still the same. Or we're going to leave that attached to the nitrogen. And this CH2, we rip off a H off that location. And since this double bond has 4 hydrogens off of it, this one only has 2, that is our product. Right. D is going to have a similar type of drawing as a possibility because I'm just going to do left and right. So if I break off the left, I'd be ripping off a hydrogen here. The ring looks mostly the same. My other possibility is we break to the right. Two hydrogens off this double bond, 3 off that one. So that's one we make. Do I like that? Actually, I see another possibility. Back up on that circling. Because I could also take one of these hydrogens off this end location. 1, 2, 3 hydrogens. So these both have 3 hydrogens. This alpha position would have been more stable to break off at first because the more substitutions. So that's the one we're going to get. That one was fun. Okay. 33. I'm going to draw the resonance contributors to show why pyridine N oxide is more reactive than pyridine towards electrophilic aromatic substitution. All right. Okay, so pyridine. Let's go ahead and put the N oxide on there. Oh, I see what's going to happen. Alright, the oxide's negative charge, going to donate N, forcing these to go up to a location. So we would have a resonance contributor double bond to the O. That's still there, that's still there, this is negative. And we're going to move that around. Yeah. It's going to move all around between these 4. But the reason that's going to make it more reactive towards electrophilic aromatic substitution is it does donate that negative into the rings. The ring itself is more nucleophilic. Alright, and what position would we expect the electrophile to go? Well, if we look at where these negatives end up, that's the spot where the electrophiles are going to be most attracted to. So it's going to be the 2 and the 4. Kind of ortho and para, but we'll find that when we put nitrogen on there, we don't really say ortho and para anymore, so it's the 2 and the 4 position. That's pretty neat. So those positions, simply because the oxygen is able to donate electrons into the ring. Oh, wow. Alright, 34. Chemical shifts of the C2 hydrogen and pyrrole, pyrrolidinium, and pyrrole are 2.82, 6.44, and 8.55. Match each heterocycle with its chemical shift. Okay, so these aren't necessarily listed in order. Okay, so so pyrrole. Oops. Excuse me. Let me drink something here. Just a second. Okay. Pyrrole. Talking about that hydrogen. Pyridine. And pyrrolidine. This one has 2 hydrogens. Okay, well, I would suspect that both my pyrrole and pyridine are going to be shifted to almost pi levels. So, like they're aromatic. So, this one's got to be the 2.82. Because those are down where you'd expect a normal CH to be. And we're near electrophilic or electronegative nitrogen that's actually deshielding them some. But that one's the easy one. Okay, so pyrrole and pyridine are going to both be aromatic. But which one deshields them most? Alright, since pyridine lone pair is out here. Yeah, how about that? Alright, this lone pair is out here, allowing this lone pair to be more electronegative, which is going to cause that to shift more, so deshield more. It's a more deshielding pair of electrons. Yet on pyrrole, those electrons are just part of the nucleophilic system, which is why this is much closer to where we'd expect an aromatic ring to be at. Do I like that? Yeah. Yeah, I'd buy that. Okay, 35. Explain why protonating aniline has a dramatic effect on the compound's UV spectra, yet protonating pyridine has only a small effect. Okay. That's a good question. So aniline gets its UV spectra from those conjugated double bonds. And if I protonate it, I have that. Pyridine Okay, I get this. Alright, so on the aniline, I have those pair of electrons there. Well, if we think back about this, we find out the biggest reason this is an activator is because this kind of donates into the pi system. And we get weird transition states that show that those electrons are sometimes shared with the ring and force the ring to take that negative charge somewhere and put it inside of it. Alright, well, those resonance structures help explain why that ring is so much more nucleophilic. It's also going to explain this property because those electrons are part of this pi system. And if we protonate them and take them away, we change the pi system. Yet I don't do that at all on pyridine because that lone pair is never part of the pi system and makes up the ring. Those are just normal nitrogen electrons. So these go away because they're part of the pi system that creates the UV spectra. But on pyridine, you don't have that same effect. Okay. Why is the pKa much stronger than ammonia? Alright, so why is it almost a weak acid by comparison? I kind of know already that the other lone pair that makes up this is inside the ring. Yet on ammonia, it's always part of a transition state. So it's always, or not transition, it's always part of a hybrid molecular orbital. It's out. Okay, that makes sense. Alright, so when this happens, we still have a pair of electrons inside the ring, still part of the pi system. So this nitrogen's only dealing with one pair of rings on one pair of electrons all by itself. The other two are shared by the carbons. And this particular nitrogen, they're both owned totally by the nitrogen. So the nitrogen cannot use resonance to hide those other electrons. So what I mean by that? Two electrons have to stay out, but I can move the other ones into the ring and move that lone pair around. So it doesn't have to stay isolated onto that nitrogen. Yeah. Okay, 37. Propose a mechanism. Well, I kind of like the idea of this getting attacked, or doing an attack, an electrophilic attack on the carbonyl. At first, HCl. Let's do this first. Yeah. I need to do more on this. Let me back up here. I've overly simplified a couple things. So let's take our nitrogen. And our carbonyl species. The first thing I'm going to show is the HCl that's listed there. Getting attacked here. Positive is on that oxygen, because it's going to make that carbonyl a better electrophile. And we are going to show that getting attacked. Going to lose that double bond. When that happens. And I will put the positive here for now. Resonance can allow that to move all the way even to the nitrogen even. But we're going to leave it there right now. Yeah, having it as a Cl here, I'm just going to show a base come in here. And we end up with an intermediate that's relatively stable. That should be an OH. Like so. Okay. Now we're going to have another acid. Could be that HCl still, it could be this thing we just recreated. Attacking here, kicking off that base. We will kick this back here, kick that up there, kick this over here. That'll drop the nitrogen, or the positive onto the nitrogen. Okay, but this is electrophilic, and it does have two of these. Not necessarily drawn in a good location right now, but that alpha, or that 2 position, can do an electrophilic substitution there. Oh, great, out of paper. But that's going to take the electrophilic ring, and we will move that back, go back to single CH2 here. And at first we'd have that and a hydrogen on there, positive and hydrogen. And this base is going to come back and rip off that H and give us back to that thing. Yeah, that's kind of clever. Neat. I do imagine you do need to add acid to get that going, because we would need that formaldehyde to be a little bit more reactive. Yeah, I think that's a good one. Alright, well, we are out of time. We've made it up to question 37. Yeah, we definitely can't do this in 5 minutes. So we will stop here for the day. I'll get this posted as quick as I possibly can. and hopefully Zoom and or YouTube will be both fine. I'll let you know if Wednesday's going to be the same way, but I'd like to be back in the classroom if possible. All right, talk to you later. Bye.